Swayam Prabha. Digital India. Educated India.
So in this lecture, we will discuss about some algorithms to conduct constant pressure MD simulations. So the original MD simulations operates under an NVE condition, as you would know. So that is when we set the Hamiltonian to be sum of the kinetic energy and the potential energy, and then when you apply the equation of motions, either Lagrangian or Hamiltonian, we basically solve a system with constant energy. Okay, so that is N, V and E are fixed. Okay, so all the algorithms we have discussed, finite difference method, correspond to following the trajectory in the constant energy surface. Then we discussed that for practical purposes, in terms of comparing with the experimental data, we often do at constant temperature experiments. So instead of having constant energy, we would like to maintain constant temperature. So then we decided that to do NVT MD simulations. So in this case, we looked at several strategies to fix the temperature. One approach is to kind of rescale the velocities at every time step so as to keep the temperature fixed at a particular value. So that is called a kind of constraint method, which refers to a constant kinetic energy simulation rather than the constant temperature simulation. And then there are other methods like Anderson thermostat, where we define a particular frequency with which we take the particle from the system and then delete its velocity, and then sample velocity from a Maxwellian distribution corresponding to that temperature, which is known as a stochastic method. Then there are other methods known as extended system methods, where we couple the system with the surrounding through some additional degrees of freedom, and we talked about Neuhauser thermostat. So the idea here is that you redefine the Hamiltonian such a way that you have additional degrees of freedom to take care of the coupling between the system and surrounding, and you can control whether the coupling has to be weak or strong with certain user defined parameters. So all these discussions we followed for a constant temperature simulations. There arises a need where sometimes we conduct experiments at constant pressure as well. So now we need to have an algorithm that will take care of the pressure of the system to be maintained at constant value. So instead of fixing the volume constant, so we will fix the pressure, and the system will be able to adjust the volume in response to changes that happens in the system. So that is what we are going to discuss today. Several algorithms we are going to discuss where the pressure will be held constant. And you will see that the treatment of constant pressure simulation bear a lot of analogy with constant temperature simulation, because the ideas are pretty much analogous. So the way we do constant temperature simulation, that can be mapped or that can be carried over to constant pressure simulation also, which means you could either constrain the system by rescaling the particle coordinates so that the pressure is held constant, or we can even take an extended system like a Neuhauser approach and then define additional degrees of freedom which can be incorporated in the equation of motion itself. So either of these two methods is possible. So let's look at all this in detail now. So the most easiest way to fix the pressure in the MD simulation is this Berenson barostat. It works in a very similar way as the Berenson thermostat, where we couple the system to an external pressure bath which is kept at some pressure P set. Okay, so you can imagine that your system, so this is basically your experimental system or the physical system. Has a movable piston here, and then it is surrounded in a pressure bath. So, whenever this pressure molecular collisions and molecular processes, and then this piston can actually move, so it can do work so that the volume gets adjusted, so the pressure remains constant. Similarly, because of some changes happening in the system, if the pressure goes down, then the piston can actually move in the opposite direction so as to keep the pressure constant. So, we are basically looking at a process where one of the valves of the system acts as a piston, and then it adjusts its volume so that the pressure remains constant. But throughout this whole process, the pressure of the reservoir is always kept at P set. So, this basically says how we would construct an experimental system to maintain a constant pressure. But this is an experimental configuration. But as you know, when we try to do a simulation at a constant pressure, we do not take the entire system. So, we do not consider the entire boundaries and boundary conditions, but rather we take a very small portion of the system, and then we build a simulation box corresponding to that particular situation, and then we have atoms in here. So, now if you look at the real experimental system, the volume of the system is adjusting, it is changing due to some molecular processes that we have to mimic in the simulation box also, or contract in response to changes happening in the system. So, we want to have a method where the simulation box will respond to pressure fluctuations in the same way that the real system would respond to. Okay. So, then what we can do here is that we can define a rate equation that describes how the pressure in the system will change with respect to time with certain time constant tau p. So, you can recollect that we have a very similar equation for Berenson thermostat, where we had defined that instantaneous temperature is catching up with the set temperature with the corresponding time constant. So, we had used an equation something like this, where the change in the temperature with respect to time is proportional to how much the temperature is deviating from the set temperature with the corresponding time constant. So, this time constant basically tells at what rate the temperature will catch up to the set temperature. In the same way, we are defining here an equation, a first order process, that says how the pressure in the system should catch up whenever there is a deviation from the set pressure. So, as you can see, when P at any time t is equal to the set temperature, then you see the dP by dt equal to 0. So, pressure is not going to change, but any time the instantaneous pressure changes from the set pressure, then we basically try to change the pressure of the system so that it catches up to the P set. The way we do that is we take the coordinates of the particles, and then we scale the particle coordinates with a certain scaling factor. In the same way we did in Berenson thermostat, where the velocities were rescaled by a factor lambda. So, here we have to imagine that the simulation box is scaled by a factor chi here every time there is some changes happening in the system, and if the volume is scaled with the parameter chi, then the coordinates or the linear edges of the box should be scaled with the 1/3 of this parameter chi, because it is a 3-dimensional system and V is proportional to L cube. So, we basically scale all the linear dimensions with the scaling factor of chi power 1/3. So, you can see that at every time step, whenever there is a change in the box volume, we change the coordinates of all the particles by a scaling factor chi to the power 1/3, where this parameter chi is a scaling factor and it is given by this equation. You can see that this is proportional to how much difference is there in the pressures between the set pressure and the desired pressure, and it also has this time constant that dictates at what rate this pressure should catch up, and then it also has this proportionality constant known as isothermal compressibility. So, if you know something about the system's behavior, if you are simulating water or ethanol, and if you know what is the compressibility factor, that can be used here to define this parameter chi. Suppose if you do not know this parameter, we can group this isothermal compressibility and this time constant tau p together, and then you can define an effective time constant tau p prime. So, it is not necessary to know what is the isothermal compressibility of the system that we are simulating. If it is known, it is little better. And simulations with water at constant pressure suggest that the time constant typically goes between 0.01 picoseconds to 0.1 picosecond. So, that roughly translates to some 10 to 100 time step, with which the pressure will set to a P set. So, if I look at the response of the system with respect to time, so whenever so you will see that the pressure will reach at different rates depending upon the tau p value. So, when tau p is, so tau p basically increases this way. So, when tau p is very small, the pressure basically goes to the set pressure very quickly, and when tau p is large, that means it takes longer time to catch up to the set pressure. So, one can do a sensitivity analysis of whether the constant tau p has any relevance or any correlation with the measured properties, and we want to ensure that this property, this time constant tau p, should not influence our results. So, some sensitivity analysis is possible to do to find what is the optimal value of tau p. This range I have given here is only for a molecular water, but any new system that you would like to study, you can try to optimize what is the relevant time scale. So, this Berenson thermostat is very intuitively very simple, and it is very easy to code as well. But only problem with this approach is that we do not know what is the sampling distribution of the system by having this ad hoc scaling of the positions and box volumes. So, because of this, we use Berenson barostat only for the equilibration period, where the pressure can be easily set to the desired pressure, and then we switch to a little more smoother barostats whenever we do equilibration, whenever we do the production runs. The next approach is one of the extended system approach. It is also known as Anderson method. So, what we mean by extended system here is that, so extended system means, so we consider system plus some the effect of surrounding through some additional degrees of freedom. With additional degrees of freedom. Now, we will not try to derive all these equations, but we will just see how this algorithm works and what are the parameters that we need to be specifying when we use this kind of a method. So, like Berenson barostat, in the Anderson method also, we think of coupling the system to an external pressure bath, which is set at P set. The idea remains the same, and this coupling of system with the surrounding basically mimics as if that there is a piston acting on the system so as to adjust the pressure. Now, we think of this piston to have a mass of value q, and then we define a kinetic energy, the additional kinetic energy to the system as q times v dot square by v, where this v dot is the rate of change of the volume of the system. We also additionally define a potential energy associated with the box, which is given by P set times V. So, you can see this PV is basically the work done whenever the system actually expands or contracts by moving the wall. So, we say that PV is the associated potential energy, and Q times V dot square, you can see that this has a similar form like a kinetic energy, where this would be like V. So, the units of Q is not strictly mass, but you will have mass times time squared, I think. So, we basically analogously define a kinetic energy for the piston, and then the potential energy because of the movement of the piston. Now, the particle positions or the coordinates are used in terms of some scaled variable, where this S here, so if I define S, it becomes R by V power 1/3. So, R is the particle position or the coordinate at any given time, and V is the corresponding volume at that particular time, and then we use always a scaled variable for each of them. And similarly, the volume is the velocity is also used in terms of some scaled variable S dot, which is nothing but V by 1/3. And then with this we can write the kinetic energy. Once you have the scaled variable like this, you can show that this becomes So we write the kinetic energy in terms of some scaled velocities and scaled positions, and then we can define a Lagrangian, which is basically which is basically the difference between the kinetic energy and the potential energy of the system. In addition to that, we also have the extra kinetic energy and the extra potential energy corresponding to this coupling. So the effect of coupling of the system with the surrounding is actually manifested through this additional kinetic energy and the potential energy defined by these. So once we have a Lagrangian, we can apply the Lagrangian equation of motion, and then we get, as you can see, we basically get the second order differential equation for the scaled particle positions. This is a second order ODE. So this equation basically should be similar to our Newton's law of motion for an unconstrained system, where m times r dot is equal to force, but here instead of r dot we have s double dot, because we are using a scaled variable with respect to this box length. And then you can see that the denominator has this m to the power v 1/3, that is because of the scaling. In addition to this force, we also have this additional term. This additional term comes because of the additional potential energy that we have fixed. And similarly, now we have to also solve the rate at which the volume is going to change, and it is also coming from a second order differential equation for the volume. So we not only solve for the scaled particle positions, but also we now solve another set of equation for the rate of change of the volume as well. So this is also a second order ODE. So we solve this to get v and v prime, v and v dot, and we have to solve this in a coupled way, and this will try to set the pressure of the system at a constant value of p equations. So a few things to discuss about Anderson method would be that this equation of motion that we discussed here, with some additional kinetic energy and potential energy, and then the corresponding change in the equation of motion, can be shown that it actually samples what is known as this constant enthalpy or NPH distribution correctly. And this piston mass parameter Q is basically an adjustable parameter. Like I said before, it basically says how strongly the system and the surroundings are coupled. And then if you keep the Q value very low, you will see that the box will fluctuate very rapidly, even for a very small change in the pressure system. Whereas if you keep the Q very large, then the system will respond very sluggishly whenever there is a change in the pressure. It will take very long time to restore the pressure to the set value. So some optimization is required to find the right value of Q, so that the system reaches constant pressure in a reasonable amount of time. So one particular study showed that this value of Q can be set to some value like 0.0027, but again, for any given system, one has to do a sensitivity analysis of how to choose Q values and whether these Q values have any correlation with the measured properties or not. So now the previous two methods basically aims at fixing the pressure in the system. In addition to that, suppose if you want to do NPT simulation, that means you want to do constant temperature at the same time constant pressure as well, then these two previous methods we have to couple with another thermostat. Typically you will see simulations where temperature is set by Berenson thermostat and pressure is set by Berenson barostat. So you have to independently select a barostat and thermostat. Similarly, you can use an Anderson thermostat. Along with that, you can use a Berenson thermostat. So basically, you can independently choose one method for the thermostat, another method for the barostat. But there are some other algorithms where inherently within this extended system approach, we can simultaneously incorporate both constant temperature and constant pressure conditions, so that we can simulate an NPT system to start with. So that such a method is called this Nuss-Hoover thermostat barostat approach. In this case also, you can see that the Hamiltonian is actually redefined to include additional degrees of freedom, so that the temperature as well as pressure can be fixed. So you can see that the first term is the kinetic energy of the system, that is the kinetic energy of all the particles inside the system. Then we have this potential energy U of r, but instead of r we are writing this in terms of some scaled variables, because the volume is not constant now. Whenever the volume changes, the particle's position will have to be rescaled. So, we often use this scaled variable s. So, in addition to this, we have 3 additional terms. So, this term comes from maintaining the temperature constant by having a kinetic energy term, and then we have an additional kinetic energy term associated with the box volume, and then we also have an additional potential energy associated with the box variations. So, we can see that we are trying to combine all the parameters or the additional degrees of freedom for temperature fixing as well as pressure fixing by having additional kinetic energies and potential energies to take care of this constant temperature, constant pressure conditions. So, since we are looking at constant pressure as well, so we use this again the scaled coordinates. Once you have this Hamiltonian, we can derive a set of Hamiltonian equation of motions, and you basically get set of equations for the scaled. This is basically the scaled particle positions, and this is for the particle momenta. You can see that our original Newton's law of motion with only Hamiltonian of the system would give you P dot is equal to just F, but now because that we have additional constraints to maintain the temperature pressure constant, we have this additional set of variables chi and eta, and we need to know how this chi and eta are going to change during the simulations. So, we get additional set of differential equations on the rate at which eta dot and chi dot changes. So, we can see that this tries to fix the pressure, and this term tries to fix the temperature. Okay. So, we end up simultaneously solving this set of equations by which the system's temperature as well as pressure reaches smoothly to the set temperatures. And a nice thing about this particular algorithm is that it is, one can actually show that when you update the trajectories, or when you sample the trajectories by solving these set of equation of motions using this particular Hamiltonian, it samples the NPT distribution correctly. In other words, we will be sampling the Gibbs ensemble accurately. So, this is basically a kind of more rigorous way of maintaining the distribution to follow closely the Gibbs ensemble by solving this. But again, you can see that in this set of equations, we have a lot of parameters to set. We have to set this parameter, initial parameter q. We also need to fix this tau p, also kind of a time constant that tells how pressure will be fixed. So, again, one has to do some optimization to find what are the relevant parameters set to use Neusuver method as well. Now, the previous method, the Berenson thermostat or Anderson thermostat, the previous methods such as Berenson barostat, Anderson barostat and Neusuver thermobarostat, all of them think about this box having a fixed shape, that is a cubical shape. We allow only the size variations. But now there is an additional another barostat known as Parinello-Rahman barostat, which also allows you to change the box shape in addition to change in the box size as well. Okay. So, we have to note that this Berenson, Anderson and Neusuver. So, all these keep the box shape fixed. And it changes only the size. But in this Parinello-Rahman barostat, we have an additional degree of freedom where the box shape can also change. So, it is something known as a changing box method or changing box shape method. And as you can see in this figure, so you might start with a cubic box, but then this algorithm will let it evolve depending upon the physical process happening in the system to change its shape into different way. And this kind of a simulation is important because sometimes when you simulate a crystal system, and if your crystal do not follow a symmetry of a cubic lattice, then you will have a problem in equilibrating and sampling. So if you let the box change the shape, then your system can actually take whichever symmetry that it wants to crystallize into. So this Parinello-Rahman barostat is more suitable for simulating a crystal system for that matter. So we have to remember that this method allows the change of the box size as well as shape, and these are more preferred for crystal simulations. So here in the previous all these examples, since the shape was cubic, we could always talk about the volume, and we can talk about edge length to be 1/3 of the volume, and then the scaling can be done with this factor v power 1/3 all the time for scaled variables. But now that all this shape of the box is going to change, we are going to define a set of vectors for denoting the box edges. So for example, we can have 3 independent axes, h1, h2 and h3, and these will become now a variable. Each one of them can independently change, and when this h1, h2, h3, this is vectors of the unit cell, when they change, you can see that the box shape could also change depending upon how the h1, h2, h3 changes. So then we define a matrix H which comprises all these unit cell vectors h1, h2, h3, and using this we can define a scaled variable as r. So basically it becomes S is equal to the inverse of h times r. So earlier we would have written S is equal to some v power 1/3 times r divided by v power 1/3, where the volume was a scalar, but now we have to use linear algebra or the inversion of the matrix H to get the scaled variables S. So to get the volume of the box for some h1, h2, h3, we use this identity h1 times h2 cross h3 will give you the box volume. Like before, like the way we used Anderson method, extended method, we defined additional potential energies and additional kinetic energies with regard to change in the box size and shape. So you can see that the P times V is the potential energy associated with the box volume change, and this V here is given by this particular h1 dot h2 cross h3, and P is the pressure that we want to set at. Okay, so this should be P set times V. Similarly, we have associate a kinetic energy with the box, and we would have simply defined in the Anderson method as 1/2 q v dot square for the case of a cubic box. But now we are letting the box to evolve, so we have to use this 2 index h alpha and beta, where alpha and beta can be 1, 2, 3 etc., and we use this rate of change of these edge lengths. So with this new definitions, we define the Lagrangian to be kinetic energy of the system minus potential energy. In addition, kinetic energy of the box minus the kinetic energy of the potential energy of the box. So once we have defined the Lagrangian, and then we can apply the equation of motion, and then we get a second order differential equation for each particle's scaled positions, and similarly we define an additional set of equation for the rate at which its unit vectors of the box will change in time. And then once we solve dynamically the trajectories at any given time, we can find the components of the pressure tensor using our standard virial equation. So the first one comes from the kinetic part, and the second one comes from the intermolecular forces or interparticle forces. This is the virial part, and this is the kinetic part. So you have to imagine that in the case of a cubic box, we would have simply written P is equal to some n by V kT plus the virial times the average virial times by volume. So now all these terms are now written in a component form, because now the box is no longer a cubic box. It's going to change its shape and size, and then we write in a component forms. So this kinetic terms now takes a little more detailed expression here. Similarly, the virial form is written here. So, the Parinello-Rahman barostat, when you invoke in your MD simulations, and you are basically allowing the system to sample its shape as well as the size of the box. Okay, so so far what we have discussed is a different set of thermostats and barostats. So, on the thermostats, we have the velocity rescaling, and then we had Berenson thermostat, and then Anderson thermostat, and then Nosauer. In the barostat, we discussed Berenson again, Anderson's extended method or extended system, and then Nosauer method, and Parinello-Rahman method. So we have focused only on these methods because some are very simple to use and others are sophisticated enough and more popular. And many of the open source MD engines like LAMS and GROMACS basically have coded these barostat and thermostats, and you can use them in different combinations. So, the question is that given that there is such a set of choice of thermostats and barostats, so which one to use, which thermostat, which barostat to use. So, again there is no a general guideline, but then a rule of thumb is that to achieve a prescribed temperature during equilibration, you can quickly get a temperature stabilization by using a velocity rescaling, which is quite quick and easy because we are not using any random numbers like in the case of Anderson thermostat. Whereas on the other hand, this Anderson stochastic thermostat is much more used for equilibration because it takes the temperature rather smoothly to the desired temperature. So, if you want to be safe, absolutely safe, you do not want to take any risk, it is always good to go with Anderson thermostat. And for fixing the temperature in a very smoother fashion, which is required in case of, let us say, when you do non-equilibrium simulations where you apply a shear or when you have some heat transfer, where the temperature maintenance is very important and to be smooth, and you are not looking for some high frequency oscillations or too much of fluctuations. If you are not expecting such ill behavior, you have to use a Nosauer kind of thermostat, which is always very good to maintain the temperature pressure at the desired level. And if you want to equilibrate to a new pressure, so one can use Berenson thermostat, but then the Nosauer barostat seems to be the best candidate for constant pressure simulations. And only problem would if you were to do your own coding of MD simulations, this Nosauer extended methods, it can be a little bit more difficult. But if you are going to use any open source and if it's available, one can easily use one of these Nosauer methods or extended system methods. So, this gives a kind of a rough overview of various barostat and thermostats. And so, for your simulations, it's always good to choose one or two thermostats and barostat and make sure that your results that you're obtaining are not sensitive to which of the barostat or thermostat you're using. Because in principle, if you think about, we talked about systematic error and statistical error, and the choice of this thermostat barostat would amount to systematic error. So, it's good to run the simulations with the two different kinds of barostats and two different kinds of thermostats and ensure that you are not getting very surprising results because of changing the thermostats. Then you know that there is an issue with your sampling or the system.